Hello friends, welcome back to another part in the series The Raytracer Challenge by James Buck, where I'm implementing a raytracer based on the book by James Buck in Rust, a language I've never used before and I'm learning while I'm going along together with you. So yeah, let's just take a quick look what we did the last time. In the last session, we actually did a first render and a first creation of a real ray traced lighted result image, and let's quickly do that again. That was chapter 6, I think. So yeah, it is rendering now. Oh, we actually found out we can speed this up if we let the system use a release version, which is a lot more optimized. So let's do this, because then I can actually show it in real time here. So let's open the output PNG and let's, maybe move this in scope so you can see it. So this was our last result. Ray traced, really nicely ray traced sphere with a, I think, 4096 by 4096 dimension, and yeah, it looks really nice, and so we are now able to render Phong lighted spheres with our ray tracer, which is quite a nice achievement. So what is next in our book? The next chapter, chapter 7 actually, talks about the creation of a scene, so that we can actually handle more than one of our objects in the world. And this is done by simply creating a sort of a grouping system where we can essentially have multiple objects defined in our world and then somehow transformed and positioned so that we can use this to establish a scene which then the ray tracer can render. As a difference to the last scenes where I prepared the tests beforehand and then only copied them in, this time I didn't have, unfortunately, the time beforehand to do just that. So we will actually create the tests within this session again, but I will later in post-editing speed this implementation up a little bit so that you don't need to see me typing in all the different coordinates and stuff that we are now expecting some objects to have. So I guess this will work out as well, and we will do it this way for this session. So what is the first thing we actually need? The first thing, according to the book, we should implement is a world. So yeah, let's, even though the chapter is called Making a Scene, then we are going to build a world, which kind of makes more sense in naming things. But yeah, let's just do that. Let's create a world.rs file. Let's include it in our, let's remove the console here. Let's include it in our library so that it is compiled, and then let's start by defining, I guess, a struct which we call world, which will then hold, according to this thing here, to this book, will hold objects which we called bodies in our system, and a list of lights. So yeah, I guess we can do that as well. So let's do that. We have a list of bodies, which are essentially a body. So let's, I guess, import that. And we have a list of lights, which we call which are actually, did we implement a base lighting class thingy? I don't think so. Let me quickly check. We directly implemented the point light. No. So for now, I guess our world will directly take point lights. but we might later on, if we are going to implement further different lights, we might want to implement this in another way, maybe. Yeah, first of all, we are not storing one of those. We are storing a vector of those. And I guess... So now we have kind of our structure for our to hold our world. So the usual thing we always need is, let's create an implementation for world, I guess. And let's say this implementation will have a new function called new, as always, and it takes bodies, which is a vector of body elements, and it takes lights, which is a vector of point lights for now. And it will return a new world. Yeah, we have mismatched types there, I get that. So let's see. Yeah, we essentially only need to create a world then and put our bodies and our lights in. Yeah. And I definitely want a default implementation for that, which gives us an empty world, I guess. And then maybe we could somehow allow, we could implement functions later on to add bodies and stuff like that. Yeah, I think I want to do this. So let's implement default for world. So let's see. We need to implement the missing members. So we are simply returning a world here then, which has bodies, which is an empty vector. And it has lights, which is an empty vector. There's an exclamation mark missing, and let's format this, and there we are. We have our default implementation. Yeah, I guess that's nice. So what does the book tell us about our first test we should create here? Kind of a default world kind of stuff for tests. So I'm not 100% sure how I'm going to implement that. Maybe I will use a macro for this. I don't know yet, but let's for now do as always, how was this? CFG. I can never remember that. Tests, I guess. And then mod tests, was it? And then we can use parent, no, super star here. And why is this? Did I do something wrong? Let me quickly check how it is done here. I guess I've done something wrong there. CFG test, not tests. So, yeah. So let's do this, and then let's just define a test. Come on, a test function here. And we will call this function, what is it called here? The default world. And this is simply to test that we have this specified default world, which I will quickly implement. So now we have defined a new body, which is a sphere with a certain material, which we have defined above, which is a Phong lighting material. Which uses the defaults for every value with the exception that it uses another color, another diffuse, and another specular value than the default. And we are creating a sphere from this one, so more or less we are creating a body. Are we creating more than one body here is the question. Yes, we are. So let's call this one as 1. And we are, I guess, creating another one, which is using... Is it using the same material? No, I guess the other one is simply using the default material. So let's create one. Which we have here, and this one actually has a transformation, which is a scaling matrix. Scaling matrix 0.5, 0.5, 0.5. Oh yeah, you can see the sum. As far as I can tell to the book, this test actually should use those information, create a default world, which they are using for testing purposes, and then check that the default world is essentially representing all those information. But I don't really want to do something like implement the default. I could implement the default trait for the world to give you exactly this kind of world here with 2 spheres and one lighting, and but I'm not 100% sure I want to do this, as the book essentially is only using this configuration for tests. So I guess I will create a function called create default world, I guess, and it will return a world then, and it will simply give us exactly this world. So let's now do a world new here, and let's put in there a vector of S1 and S2. So we have the spheres there, and we are putting in a vector of the light, which is only 1. Oh, so function is never used. Yeah, it is never used. I know that. So now let's do this one here and say, okay, give me a new world. So let world equal create default world. Let's do this. Now we have a world, and now we can assert. So now we have a function to create our default testing world. So let's write our first real test, which is essentially fn. So intersect the world with array, because we want to be able to intersect our worlds then with array of our choosing, which we are firing through the whole scene to see where intersections are with any of the world objects. So now we have array. Let's import this one. So let's scroll this up a little because you can't even really see it. So now we have this array. And now we are getting our intersections. So let's get them from the world. So we have 2 objects, 2 spheres in the scene, and this specific race should intersect both of them. So we should get those intersection parameters here. Those 4 intersection parameters are within those intersect result. So for now, let's just see that we are implementing this intersect method. So yeah, I guess let's intersect. Let's implement world pubfn intersect, which gets array and returns intersections, which we need to import, of course. So, oh yeah, and ray we need to import here as well, and then we can actually remove the import down here. So yeah. Mismatch types, yeah, of course, because we are not returning intersections yet. So what we need to essentially do is we need to loop through all our bodies, calculate intersections, possible intersections with them, combine all of these results up and return them. So maybe we can simply do, we need of course a self reference here, so we can access our, we want to do self bodies, and we want to maybe map those things, and we could map those as body, I guess, and then we could have those. The method map does not exist for struct vec body. Oh, yes, I guess I need to retrieve an iterator of the vector here first. Let's check. If we now get those bodies out of there, we could simply do body dot intersect, and we put the ray in there, and then we are already. Do I need those curly braces there if it's only a one-liner? I don't think so. So now we should have actually a list of those intersections in there, and I would really much love if I could do something like a flat map, but I guess I can't, because let's see why. Maybe we can implement this for intersections. The trait iterator is not implemented for intersections. Yeah, required because of the requirements on into iterator for. Yeah, but couldn't we just implement? I guess we could implement iterator for intersections, because why not? We could just pass it through to the data here, which is a vector, which essentially implements iterator. So how is this gonna work? So let's implement into iterator, I guess, because that's a lot easier for us to implement, because we can simply take the one from the inherent data struct we have there. So let's implement into iterator. Let's remove all of this and let's tell the compiler that we want to implement the missing members. And I need to take a look at what those are. So into iter would be an iterator. Do we really need to define this? I don't think that we need to define it. So let's check. Into iterator, the item would be an intersection here. And into iterator would be... okay, so it seems to me we need to implement this one, but this one would be an iterator then. Not an iterator, but an iterator. So, and then we would, I guess, simply return self data into iter here. The value of the associated type item from trait iterator must be specified. So is this like, do we need to do a self item here, like a template or what? No, okay, not. So what's the, how do we do this? Let's just do that. Oh, was it into iter? Yeah. Okay, so so now this should actually be iterable. Let's see. So now we should be able to do a flat map here. And oh, this works now. So what is this now? This flat map now is an... we have now a flat mapped iterator. Nice. So we can... couldn't I just here tell the one to collect, because this should actually be possible. So now I should have, yeah, now I should have a list of intersections there in a vector, and now I should essentially be able to just do an intersections new and put the intersections in there, maybe? Maybe I should call them XS, as I'm doing a flat map now, and this should work out now. So this is a vector of intersections then, which I'm creating here by flat mapping all the intersections of all bodies. Then I'm collecting all of those, and then I'm essentially just putting them into the intersections again, which then sorts them and gives me an intersections object which contains all of them. So yeah, let's maybe check if this works by running. It doesn't work, I guess. So fuzzy NE, font for reference integer in the current scope, fuzzy equality. So this is somewhere in the world file. So I'm going to, what I'm doing, oh yes, it is completely right. We have not implemented this for integers, because why should we? But we need to, of course, tell the system that we want a floating point there. So I guess let's try again. Yeah, and now the tests are passing, which means let's run cargo test world, I guess. And there should actually be... yeah, that's nice. So it is intersecting with the world, and it is obviously returning the right and correctly sorted intersections, which is kind of nice. So yeah, this one works, I guess. So let's maybe do a commit there. So what's the next thing we will do? The next thing is actually that, yeah, the book is telling us a sort of preparation work is in order, because if we go back to our rendering information here, where is it? We kind of calculated, Was it in our lighting function? I guess in our lighting function. Let's see. So our lighting function takes all of this information, like the position of the intersection, the I vector of the intersection, the normal vector of the intersection. And all of this is then calculated currently in our main loop here, which takes all of those intersections, extracts the hits out of them, and then calculates all of those information, which is of course okay, and then puts them into this lighting function to get back the color there. So this is nice, but the problem with this is that if we are going along with our ray tracer, we will need all of those values, like the position, like the normal vector, like the I vector, and like some other values which will be added to this a lot of times. And it would be kind of, we shouldn't compute them over and over and over all the time. We could compute them once we need them, and then store them for later usage just to speed things up, because otherwise things will get horribly slow and we are not really optimizing here anyway. So let's take a look at how to do this. The book does this by creating a sort of how is it called? It's called pre-computed state. So you are actually doing a prepare computations, and you have a computations object, and then you get all those properties inside a computations object for a specific intersection. I'm not 100% sure I like the way that this is handled. I understand why it is done, to be mostly flexible with all kinds of programming languages, but I'm not sure I really much like the way it is done. Hello, a short intermission from the future. In the next 2 hours, I tried to create a transparent caching layer in between the intersection calculation and all the consumers which essentially needed the data layer on. I wanted to create them lazily when they were first needed, and then just return the cached result once the requests were coming in. Due to the kind of memory management Rust provides and does for us, and the checking it does on memory allocations and moving data between different sections of the code, this actually turned out to be quite hard. Even though I found a way in the end to do this, I decided that the added complexity of doing it this way wasn't worth the magical and better usage maybe of the API. Therefore, I just decided to go along with the suggestion the book originally gave us and use a computed value structure which is explicitly computed and then used. Furthermore, I'm planning on doing some short Rust videos containing all the information I've learned, like how do the basics work, how do you install Rust, how do you use vectors, what are structs, what are traits, and stuff like this. Those will be most likely quite short videos, which I will show you in the future on this channel. So please don't forget to subscribe, and please give the video a thumbs up if you liked it. And now back to the original me doing all the development of the ray tracer. Okay, so now we have changed this, and then we can, I think, go ahead and add some add this calculation structure. I'm not 100% sure where we should put it. As it is directly connected to intersections, we might want to put it in the same file. However, we might not want to do this, because I think we will add different other calculated values later on. So I guess I want a separate file for this, and we could call it Precomputed Intersection, or Precomputed Values, or Precomputed Hit, or I'm not 100% sure. Let's just call it Computed I guess I like computed hit. Let's call it computed hit for now. So let's add it to our lib file here and include it so that it can be used. Pub mod computed hit. So let's get this one in here. Let's define a struct which is called computed hit. And yeah, I guess this computed hit struct should derive some things, as always. It should, of course, derive debug. I guess for now it should derive clone and copy, because currently it will only hold quite simple values. We might need to... Maybe we want to hold out on the copy here and specify that it can only be cloned for now, because I'm not sure that we will always only have those kind of types which can simply be bit copied in there. We will see. So yeah, what did we have in there? We actually took this from the chapters file. So let's do this again. So let's more or less get this stuff out of here. Let's put it in there, and then let's just comment it out, and then we can start implementing stuff like we had. Yeah, of course, we had the position there, which was a tuple. We had the normal vector, which was a tuple, and we had the I vector, which was a tuple as well. So now let's import tuple. Yes, import it, please. Thank you. And now we would need, I guess, a computed hit, which can be an implementation for this one so that it can be created. Yeah, I guess so. Computed hit, not hot hit. It is quite hot here, but I still want to implement a computed hit. So yeah, I guess then we have an fn new here, which takes a position, a normal vector. Do we want a new here? Or do we want the computation function to simply fill this stuff up? No, I guess we want this one. So this one gets a tuple, this one gets a tuple, this one gets an IV. Or are we actually moving the computation here? That would be a nice idea to have a function here, which is kind of like create one of those things given an intersection or something like this, and then it can calculate all the needed information within itself based on the intersection. So it's not only the data container, it's as well holding the information to store all of this stuff. We could do that. Yeah, but I guess we won't now. Let's just get something going here so that we have something ready. We can refactor it anyways later on. So this one will be a simple creation function which takes the position, the normal v, the iv, and returns this. So yeah, I guess we now have this. Yeah, it is never used. I'm aware of that because it is not public. And the struct should be public as well, I guess. So now it's not telling us that it is not using this stuff anymore. So, okay. I guess for now that is enough, and we will take this information here to our intersection, which should be able to give us this pre-computed information. So an intersection should actually be able to provide us with so an intersection should actually have a function. Should we call it pre-computed or computed? Just computed, or maybe just get computed hit? I guess get computed hit then. I have no idea what the book actually says. I could look it up there. Yeah, let's look it up there and check if maybe this gives us an idea about a more prepare computations. It is called. I like get computed hit actually better because that tells us what we are actually doing there. So let's do this, I guess. So yeah, I think we need to then calculate some of those information here. So we should actually have a self-reference here, not percent sign, but an ampersand sign. So let's do this, self.ray, and calculate the position from... Oh, that's interesting. Is this... Oh no, this is self then, simply. Okay, so... and here we have a self body, and we calculate the normal at the position, and the I vector is the inverse of the ray direction. So yeah, let's format this. And now we can simply return a computed hit new here, which takes all of those information, normal vector and I vector. No, and now I need to import this one, of course. Great, yes, import this one. I see. So now we have this function which gives us a computed hit from a... Yeah, from a... I like that, from an intersection. So now we should be able to change this here up and just do... yeah, I guess let computed be hit dot get computed hit. Maybe computed hit is not the best wording there, but yeah. And so now we could do computed dot position, computed dot I value, and computed dot normal value. We cannot. Field position of struct is private. Oh, did we not define them as... Oh, we did not define them as public. So let's do this here. Let's define those as public quickly, and now this should actually work. And yeah, so now we have used those pre-computed values, and we could actually reuse them. I've just quickly reformatted the code, and it obviously does it in a... I'm not 100% sure I like the formatting, but yeah, why not? So let's run the tests. They are still running, and let's do a cargo run binary chapter 6, was it? Let's maybe quickly change the color of the sphere again, just to make sure that we yeah, that we are creating a sphere with the right right data. So let's maybe do this. So let's render this. Oh no, I wanted to do minus minus release here, definitely. So it is speeding up things a lot. I need to remember that. So I definitely want the optimizations for this one. So let's move this one in here. This should be a nice, yeah, a nice shiny blue. So it was rendering correctly, and it used the computed values here. So this does still work. This is nice. So I guess let's... or do we want to... Are there actually tests for this inside the book? Let's check. If there aren't, I would like to have some, I guess. On an intersection. So maybe we should simply call this thing computed intersection, and then, yeah, I guess we should. Oh, maybe I could. Can I actually refactor this one? Intersection. Oh, that's nice actually. So let's rename this here as well, intersection, and yeah, it will. Nice. Did it just do this Oh, it did this refactoring for me. Oh, that is nice. Yeah, I guess it fixed all the imports then as well. So yeah, it did. So this is nice. I like that. But I'm not sure I want now get computed, but maybe we just want computed here, and it returns computed intersection. I guess that would be a feasible name then. Maybe. I think I will go with get computed. I like it if things say what they are doing. Where did we need to change that? Here we need to change the... Where is our... Oh, no. It is, of course, implemented on the intersection. So this one will be get computed then, I guess. So now it will return as a computed intersection. So yeah, okay. So the question here is, should we maybe do something like put the intersection itself into this here as well, so that we can actually back reference this one, maybe as an explicit reference? I would like that, I guess. Let's check if this is feasible. So let's check if we can do this, or if the borrow checker then intersection doesn't like what we are doing there. So cannot find type intersection. Yeah, we need to import it, of course. Import from intersection. There we go. So missing lifetime specifier. So yeah, we could actually define that an intersection, that this one needs to live as long as this... Yeah, I guess we want to define that this computed intersection can only live as long as, or for as long as this intersection itself lives. So the question here is, can we easily do this without having to now then specify lifetime everywhere? Let's check if this can be done. Yeah, I need now to specify this one here, I guess, and here again, and there again, I guess. So now we have this one. Is this actually going to work if I now tell this one I want self in here? Does this work, or is it... Okay, so this works, and now this works as well, seems to me. So could I do, let's just do, this will of course do nasty things, I guess, now, but let's check. Let's do, what was it, question mark, I guess, and let's just get computed intersection. Can I access this here now? Well, it seems to work, so let's try this. It will completely... Oh no, it does not. Yeah, it does. It will fill up our screen, but it obviously can access this intersection, with in turn then has the sphere and stuff like that linked to it. So yeah, I guess this works out. So let's kind of remove that here again, because we don't need it. And yeah, I guess now we have all those information here. We have refactored this one. Are our tests still running? Let's check. Cargo test. Okay, they are. So now we can actually go ahead and create this computed intersection test I was talking about, just to make sure that it is... no, not that it is storing data. That would be kind of silly. We need a test here which tests that the normal vector and stuff is right calculated in the precomputed intersection. So we need a test here. It should be an fn, and we can call it precomputing the state of an intersection. Precomputing the state of an intersection. And So yeah, I guess this is now working. So we have pre-computed information with regards to an intersection. So let's commit this, I guess. And the most important thing, the new structure. So pre-compute intersection state/data for later usage. The pre-computed state will help us to reduce rendering times in the future once the computed intersection values are needed multiple times and are growing in size and number, because we will have later on more than those three informations attached to something like this. So let's push this and yeah, let's see what's next in the book, because we have one specific case we didn't really take care about until now. And we actually want this information stored nevertheless. And that is what happens if our ray starts from within an object, within a body. If it is inside the sphere and it will go out there, the first hit will be the outer shell of the sphere, of course, but from the inside. So we don't have this information actually now, and we need it later on to do correct shading and testing within the world if we are colliding from within an object or from the outside of an object. So we could easily do this now and add this here. We will add the public property inside, which simply says to us that we are inside of a certain body, which is a Boolean then. And we will add this one here and call it inside as a Boolean, and of course we will add it here. And more and more I'm thinking about those simple data kind of structures, holders, however you might call them, and thinking about that these new functions don't make a lot of sense there, but yeah, I'm not 100% sure. So yeah, let's implement this now. Should be, where are we? Should be created here, of course, and it is easily created. Inside equals. Essentially, what we need to calculate here is if the normal vector of the surface, which is going away from the sphere surface to the outside, is in opposite direction of our I vector. So if we are looking at this thing and it is in the opposite direction as the normal vector, we are obviously looking at it from the inside of the sphere, because the normal vector is so if we are here and the normal vector is somewhere here and pointing outside, our I vector would be inside from the sphere part to our origin point, to our eye. So if they are going in opposite directions, we know that we are essentially looking from the inside to this thing. So in order to calculate this, we can easily do something that is the dot product. We can get the dot product of those two vectors, because the dot product will be the cosine of the angle between the two vectors. So if there are in opposite directions, yeah, essentially the cosine would be negative. So in this case, we can easily check that if the dot product of, let's see, the I vector, the normal vector, I guess, normal vector, dot I vector is smaller than 0. Yeah, essentially this should be already defining if it's inside. And now we need to take some other thing into account. If this thing is inside, we want actually the normal vector inverted, because we want the real normal vector to be calculated in order to then light the sphere correctly, yeah, so that we can shade it from the inside. That would need to then point into the other direction, because we are always pointing out, but now we need to point in. So let's then just say that the normal vector now should be the normal, or can we need to define another normal vector here then, don't we? Or can we actually make this one mutable? I could make this one mutable. So if inside, so now it will tell me that I don't need those brackets there. If we are inside, let's just get the normal vector and negate it so that it points into the other direction. So essentially this should then define the correct computed intersection. And are our tests still running? What did I do there? Oh yes. So let's add this one, just a new shell. So I needed to get my SSH key authentication from memory. So yeah, we pushed this one. And now let's see that we are... what did I want to do? I wanted to run the tests. Let's run the tests. They are still running. Nice. So now let's add a test which checks this inside thing. Which will mostly the same than this one, I guess. The hit when an intersection occurs on the outside. We are copying this test and telling the system when an intersection occurs on the inside. Let me remove the shell here. So if it is on the inside, then we are currently using a different point. We are just starting in the middle of our coordinate system because that's the middle of our sphere. We are pointing into the right, into the same direction. We are creating our intersection at position 1 with our body, and now we get the computed one, and now this should be true, and we should be able to check that our normal vector should essentially be a tuple, which is a vector, and it should have the following values. It should have 0.0, 0.0, minus 1.0. So yeah, this should work out. Let's test this if we have done it all right, and we have. So let's add this as well. Computed intersections, git add source, intersection, git CI, implemented computation of inside body hits. So now we have this as well. We can push it as well. And now we could go on and actually implement on our world the shading and go on and yeah, do that. So let's take a look at where we stopped there. We had this intersection which was working with a world, and maybe it would be a nice thing now to be able to shade, to tell the world that we need kind of a shading information. The thing that we do here essentially with our hits. We are taking the hit from the body, we are getting the material, we are letting the material calculate the lighting and giving back this information. But on the other hand, essentially what we would like to do is to tell the world that we want shading for a specific point, so that we could get this hit and say, okay, give me shading information for that, so that it would actually query automatically the right thing. So this again, let's create a function called color_add. And the color_add function, in my opinion, should take array. Let's take a look what it should take here, essentially. Yes, it takes array, which makes absolute sense. So let's get array here, and it's returning a color value. So now let's implement this, and let's add an fn there to make the compiler happy. So now, what do we need in order to get this color? We obviously need to intersect our world with array. So we already implemented this here. So let's get those intersections. So let's get xs. We need, of course, to. I always forget to reference the self here. We need to get self intersect with the array. So yeah, let's intersect there. Then let's get a hit from this intersection, so we can actually get this one. Then we get the computed values by telling the hit we please want to get the computed Wait a second. Why doesn't the hit has get? Oh no. So yeah. So we need to do if let hit is some hit. Because only then we have we really had a hit. We might not have one. So if we don't have a hit, we can simply return color black, maybe. Yeah, I guess we can simply return color black. So let's do this. And once we got a hit, let's get the computed data values here by hit get computed, which now should work actually. Didn't I guess I defined the wait a second. Let hit. We did this exactly like I'm still not. Oh yes, okay. I'm always doing this matching inside an if the wrong way around, even though it makes absolute sense to have it like this here, because we want the pattern matching to extract from the sum enumeration this inside data we have there as hit. And yeah, so now this should actually work. Mismatch types expected. Yeah, we are not finished yet. So now we have those computed data values. So now we can actually, let's get the material, I guess, from the hit, like hit. Let's get the body, and then let's get the material. We can ask the body for it. And now we can tell the material that we want to light this thing. And now we have a problem, a kind of a problem. We haven't yet implemented any possibility to light something up using multiple light sources, and I don't want to implement this for now. Our world actually accepts multiple light sources, and we will, I guess, later on implement this one. It's not part of the book, I think, but it's kind of easy to implement it. You only need to calculate the light sourcing based fonct shading stuff for multiple light sources and fire multiple rays into the light sources then to calculate stuff. But we haven't implemented this yet. And yeah, maybe I will do this as a bonus video afterwards. I will see, because it is not that hard. But for now, I guess I will simply take self lights. I will always take the first light, and I will write a to-do here, which is to do implement proper lighting using multiple light sources. So we need to do this, and then we need the essentially the positions. So we need the point, we need the I vector, and we need the normal vector here. And then we are actually finished. We have our color add function, which now goes ahead, intersects the ray with the world, gets the first hit, extracts the computed data, gets the material, does the shading, and then returns the proper color there. And we are not using this here anymore. Yeah, I guess we are not. So actually, we now have implemented this function here, and so we can actually create tests for that. We actually have a world which we can where we can put objects in and ask the world if there is an intersection. If we are providing it with rays and proper information about how to calculate this. And this is actually something we are going to tackle the next time, because for now we have quite the work done here. We have our world, we have our pre-computed information here, and the next time we will take a look at how we can actually calculate where we are looking from into our world, so that we can actually change our eye position in a way that it makes it more flexible for us to kind of define a world and then say, okay, I want to look at it from this angle or from this position or from the other side or stuff like that. So this will be what we will be implementing next. But for now, I guess we made quite the improvement here to our code by implementing this world. So let me quickly do a status here and add this one. So let's just commit implemented function to retrieve shaded color for arbitrary ray fired through the world. So now let's put this in one line. Yeah, I need it a little long, but I don't care. I know it's a little long. Trying and actually failing to implement something like this this caching system I wanted to do, and realizing that it might not even be the wisest thing to do actually. So yeah, so I'm quite happy with the outcome of this session. I've learned a lot, and I've played around a lot with stuff, and we have started implementing our world to be then later on rendered and to have the possibility of having multiple objects in our scene, which is obviously the next step in the evolution of our ray tracer to define more complex scenes. Furthermore, we have done the first steps in ways of maybe later on optimizing our ray tracer by not doing all kind of computations over and over and over. So yeah, this is something I like very much as well. Yeah, so thanks for joining me again in this session, and I hope you will be there the next time. Please leave me a comment if you have any thoughts about what we are doing here. Please press these thumbs up button if you liked what you saw here, and yeah, subscribe if you want to be informed once a new session and episode is out there, so you will directly be notified. And yeah, see you the next time. Bye!